Can anyone confirm? Am I audible?
Yes, sir.
Okay, fine. So let's start for the today's session. So it's from GATE 2020, Control Systems Instrumentation paper, technical question 14. So the closed loop transfer function of a control system is given by C of S upon R of S, where C of S is the output, R of S is the input, and this is the system 1 upon S plus 1. For the input R of t equal to sine t. So the steady state response C of t is which of the options will match this the question we have to find. So as C of S upon R of S is given as 1 upon S plus 1 and R of t is equal to sine t. So let's just take this R of S. Basically we have to convert this R of t into R of S and take it on the right hand side. So C of S will come as 1 upon S plus 1 into 1 upon S square plus 1, where 1 upon S square plus 1 is the Laplace transform of sine of t. Now by just splitting this into a partial fractions, so we get this expression. You can do the mathematics on yourself on your notebook, but this is what it comes by splitting this into partial fractions. So C of S comes as half into 1 upon S plus 1 minus S square minus S upon S square plus 1 plus 1 upon S square plus 1. So if you take inverse Laplace transform of this partial fractions, we get C of t as 1 by 2 into e raised to minus t minus half of cos t plus half of sin t. Now it has been asked at steady state. At steady state meaning when time a long time has passed, uh, basically at time t equal to infinity. So when we take this c of t which we got in the previous expression and just rearrange it a little bit. So before we apply t equal to infinity, let us keep this as same, half into e raised to minus t minus 1 by root 2. We just take 1 by root 2 common and make this 1 by root 2 into cos t plus 1 by root 2 into sin t. Yeah, one small bracket is mistaken here. Yeah. So when we put t equal to infinity here, this term goes to 0 and this two terms amount to uh, 1 by root 2. This 1 by root 2 is missing into sine of t minus pi by 4. Okay, so this D option matches this answer to this question. So any doubts in this?
No, sir.
Okay, yeah, so D option is the answer to this question. So let us look at the next question. This is again a question from control systems, GATE 2020 instrumentation, technical question 37. So system shown in figure A is having time response y of t to input r of t equal to 10 u of t. Basically it is a step change of 10 units as shown in figure B, and u of t being the unit step input. Both k and tau are positive. The gain k of the system is, so this is the system, r of t is given as 10 u of t, and y has to follow that, but y is following only till 8. So basically control objective of the control system is to follow the input. So input was 10 into u of t, basically it had to follow 10, but now the response is given as it is following 8. So directly by looking at this question we can see that there is an error in this control system. It wanted to go to 10 but it is going till only 8. Okay, so as we know this, in the previous week or the week before that I had taken a detailed derivation of a steady state error, how it is coming, this expression ESS is equal to limit s tending to 0 s r of s upon 1 plus g of s, where g of s is k upon tau s plus 1, and ESS basically its steady state error is 10 minus 8. Basically 10 is the reference which is given in the question, and minus 8 is the final value. So steady state error is 2. So when we substitute these values, s into 10 by s, r of s is the input, 10 by s is the step change of 10 units, upon 1 plus k upon tau s plus 1. So now just put ESS as 2 and s equal to 0. We get 2 is equal to 10 by k plus 1, and therefore k is equal to 4. So this answer was the answer to this question is k equal to 4. The gain k is 4. So any doubts in this question?
No, sir.
Okay, so I hope you understood this question. Okay, one sec. The question is yeah, fine. So again, next question, GATE 2020 instrumentation. It is from control systems. Technical question from technical questions number 20. A second order system has closed loop poles located at s equal to minus 3 plus j4, basically complex conjugate roots. The time t at which the maximum value of step response occurs. So this is the typical second order system where the open loop transfer function is omega n square upon s square plus 2 zeta omega n s, and when we close loop it, when we close it with a negative feedback, the c of s upon r of s comes out to be omega n square upon s square plus 2 zeta omega n s plus omega n square, which is shown in the bottom left. So when we take roots of this denominator of this expression, we get roots as s is equal to minus zeta omega n plus minus omega n zeta square minus 1. So the value of the zeta determines whether this roots will be complex or real. So if zeta is between 0 to 1, this will be negative under root, therefore it will have a complex roots, and if zeta is greater than 1, it will have real roots. So basically that is the definition of second order control system, where if zeta is greater than 1, it will have real roots, and we call it as a overdamped system. If zeta is between 0 to 1, we call it as a underdamped system. Okay, so that is the definition. So if zeta is between 0 to 1, this red colored figure, we just reshuffle this and we take j sign outside, because we know the answer is going to be complex if zeta is between 0 to 1. So we write this as zeta omega n plus minus j of omega d, where omega d is this term, omega n into under root 1 minus zeta square, where omega d is the damping frequency. Omega n is the kind of, we say, the resonant frequency. So the time response of this second order system comes out to be like this. This is a very long derivation, but you can find it in any standard textbooks in Norman Nice and any other Nagaraj Kotari, M Gopal, sorry, not Nagaraj Kotari, M Gopal or Norman Nice. So this derivation you can find, where omega d is what I explained in the previous slide, this omega n into 1 minus zeta square, and theta is cos inverse zeta. So this is the time response, where this is a time dependent term which exponentially decays, and this is the denominator, and this is the sinusoidal oscillations term, and u of t is the input. So it has been asked that at what time this peak occurs. Okay, so TP is the notation that is denoted for time to first peak, and MP is the maximum overshoot. So when you differentiate this C of t with respect to t to find at what time C of t goes to maximum, you differentiate this and make it to 0, you will get that TP comes out to be pi by omega d. And when we substitute pi upon omega n and to under root 1 minus zeta square, and if we go back to previous slides, the in the question the roots were given as minus 3 plus minus j4, and here I explained that the roots are like this, minus zeta omega n plus minus j omega d. So they were given in this form only, minus 3 plus minus j4. So omega d is directly given in the question as 4 from this, and zeta omega n is given as 3. So directly you can substitute the value of omega d here, where Tp is equal to pi upon 4, and therefore it is 0.785 is the answer Tp for this question. And there are multiple other notations: settling time, rise time, that and maximum overshoot MP. So I'll suggest you guys have a look into that formulas as well from some standard textbooks, and if you can kind of memorize them, then that will be better, if because such questions will come for 1 or 2 marks and you can easily save time on that, because these are standard answers. Settling time is a pretty much common question. So this is the answer to this question. Time to peak is 0.785 pi by omega d. Okay, so any doubts in this question?
Clear, sir.
Okay, fine. So these were the three questions I planned for today. I don't have any other questions. So
Yes, sir. I have one question from the mock test. If I'm allowed, I can share. Can I share my screen?
yeah, one sec, I'll stop sharing.